Welcome to the next lecture in BJT amplifiers. Previous lecture we discussed about the common emitter amplifier. In this lecture we will see what is common collector amplifier. The other name is emitter follower. When we talk about the voltage gain of the common collector amplifier, it is approximately 1. The meaning is that there is no significant amplification. Whatever the input we give, the same output we get, or there is any phase inversion. So if we talk about the input resistance, it will be high and it is suitable for the application that involve impedance matching. When we talk about the current gain, it is also high and hence useful for current amplification process. Phase inversion is not there because the output is following the input and the output voltage matches the input in both in terms of the phase as well as amplitude. Hence, the name of common collector amplifier is also known as emitter follower. The input signal, which is in the form of AC, is given to the base of the amplifier via a coupling capacitor. So here we have the coupling capacitor C1 and the input is given to the base terminal. The output signal is taken from the emitter. So here we have the emitter terminal. So we will be taking the output, which is also AC, from the emitter, also coupled via a capacitor. So here you have a capacitor C2 from which the output is capacitively collected. The collector is at AC ground. So we can see here the collector terminal which is at AC ground and no effect is there on the AC signal. If we calculate the voltage gain of the common collector amplifier, so voltage gain, it is the ratio of output voltage by input voltage. So we need to calculate what is the output voltage and input voltage of the common collector amplifier. So output is basically the product of the current which is flowing in the emitter, which is IE, and the emitter resistor RE. Whereas the input voltage which we are giving in the base is IE plus the sum of the resistances of the emitter and the AC emitter resistance. Now the voltage gain we can calculate taking the ratio of the output voltage by input voltage, which comes only in terms of the resistance. And here, since the denominator is greater than the numerator, so the value will be less than 1. And here the resistance of the emitter is the parallel combination of the actual resistance and the load resistance. So voltage gain we can see here is approximately equal to 1 because the emitter resistance RE will be greater than RE dash. So this circuit we can use transistor equivalent circuit, which we have seen in the previous lectures too, the R parameter circuit, which can be used to determine the voltage gain. If we want to find the input resistance, which is usually high and it is useful for this type of circuit to be used in buffer, and hence it makes the common collector amplifier circuit to be useful in buffer circuit. The input resistance which we calculate in the base is basically the input voltage by input current in accordance with Ohm's law. The input voltage we are giving at the base, so input current also we will measure at the base, and we can use the formulae to find the voltage and the current. Now here we know that the meter current is approximately equal to the collector current, which is equal to the current gain beta multiplied with the base current. So if we put it in this equation, simplify the expression, we get approximate expression as beta multiplied with sum of the resistor of the emitter and RE dash. If a condition occurs where RE is greater than RE dash, then you have the input resistance of the base is approximately equal to beta AC into RE. So this is what you have the resistance input at the base terminal, but when we need to find the total resistance, we have to take the voltage divider, which is R1 parallel to R2, and again this resistor of the base also taken into account. So the equivalent resistance will be the parallel combination of these three resistors. If we remove the load, then we can calculate the output resistance as approximately value of RS by beta parallel with the emitter resistor. And current gain and power gain also we can calculate. Current gain is basically the output current, which is the emitter current, by the input current, which is taken at the base. So it is equal to V in by R in total. So the power gain is the product of voltage gain into current gain. Voltage gain since approximately equal to 1, so we can say that power gain is nothing but the current gain itself. One important type of circuit in amplifier is basically the Darlington pair. So what is the necessity of this circuit is the current gain beta is a major factor in determining the input resistance of an amplifier. If we have higher beta, then it will improve the input resistance. So two transistors which are connected in Darlington configuration. So here we can see this is the transistor T1 and this is the transistor T2, which are connected in Darlington configuration with the current gain beta AC1 and beta AC2. If we have the connection, so the emitter output of the first transistor is connected to the base of the second transistor, and the collector of transistor T1 and transistor T2 are given the common supply. Here the first transistor emitter current, if we want to calculate, so that is equal to beta AC1 multiplied with the current of the base in the transistor 1. Second transistor, similarly we can calculate the current which is flowing in the emitter, which is beta AC2 into IE1, because this is the same current which is coming in the base of the transistor 2. So that is equal to the product of the two current gains of the transistors multiplied with the base 1 current, which is in the first transistor. The effective current gain for the Darlington pair now becomes beta AC is the product of the two betas of transistor 1 and transistor 2. And the input resistance in this case will be again the product of the betas multiplied with the RE value, which is the resistor of the emitter which is connected to the second transistor. Assumption we do as the RE dash value is always less than RE for the simplification process. One important application, let us try to see about the Darlington pair configuration of transistor Q1 and Q2 connected when we have a common emitter amplifier, which we have discussed in the previous lecture. What is common emitter amplifier? Now this is having 1 kilo ohm as the collector resistor. So here you have the collector resistor which is 1 kilo ohm, and there is a load which is connected at the output. So here you can see a load is connected in the form of the speaker. So it is 8 ohm load speaker, and that is a low resistance load. The speaker is capacitively coupled to the amplifier output. So here you have the capacitor C2 and the load is connected. So it is capacitively connected, causing the load to appear in parallel with the collector resistor. So the collector resistor what you have is basically coming in parallel with the load resistor. So collector resistor and the load resistor will give you the total resistance of the net summation of parallel resistance calculation, which comes to be 7.94 ohms, taking this example of 1 kilo ohm and 8 kilo ohms. Now what impact do it has on the voltage gain without the load? If we can find the voltage gain, so that is equal to RC by RE dash, which comes to be 200. Now if we have the load of 8 kilo ohm resistor, then the new voltage gain, which is RC by RE dash, now become 1.59. The conclusion is that the voltage gain is significantly reduced from 200 to 1.59 due to the low resistance of the speaker. So the resistance of the speaker is low, so the voltage gain has reduced from 200 to 1.59. So the solution what we can discuss here is that we use an emitter follower configuration with a Darlington pair to buffer the amplifier and the speaker, restoring the voltage gain and preventing any excessive loading. So if we have only the emitter follower, the problem will be there, but if you use the Darlington pair together, then it will be acting as a buffer with the amplifier and the speaker, and you will have the voltage gain which is stored and without having any excessive loading. So this is the third part of the BJT amplifiers, where we have discussed about the common collector. next discussion we can have on common base amplifier, and that will complete the BJT amplifier discussion. Thank you for now.